right, well, I guess Rocky Mountain asked us to come up and do the training on the boilers today. Did you guys get a copy of the agenda? Or is that just for the...
I got a copy
just
of
for
it.
you guys, okay. I'm going to try to stick to this as close as I can, but
Okay.
you guys have slotted me for an hour and a half. We can talk for 20 minutes, we can talk for 8 hours. One of the things that I was going to do here for the first part, in the outline of what the training would include, they wanted a basis of design to talk about the operational requirements and the criteria of the system. And I know I've been down here with you guys teaching some other classes. We did some expansion tank class last. But so what I thought we could do here, if you guys are interested, is talk a little bit about condensing boilers. I know you guys have boilers on your facility. Are these your first condensing boilers that you have, or do you have others? Okay. So if it would help, I thought we could take maybe a half hour to begin with and just talk about the whole process of combustion. Again, I'm part of another company where I travel North America teaching high efficiency HVAC seminars. So we can talk about the process of combustion, what occurs, why condensing, where the condensate comes from, what does it do to the system, what does it do to the boilers. You guys interested in that? You want to go over some of that stuff too?
Sure.
I see some of you asleep and I see some of you. Okay, well, let's just do it a little bit. Is it okay if I use this up here?
That's what it's there for. Yeah.
Okay, excellent. First of all, again, I don't want to get into too many details, but I want to just get into the whole process of combustion. You guys have just, you're now using boilers that can get up to 99% efficiency. Back in the day when I first got, when the company that I was working for transferred me to Boise, Idaho, all of the engineers, I would say 95% of the projects that I saw being sold were around a condensing boiler. And so I went to the engineers and I would say, well, why are you specifying condensing boilers on all of these projects? And they said, well, haven't you seen the literature? It says 99% efficiency. And I said, well, yeah, but look at the small letters that say up to 99% efficiency. Just because you've spent twice the amount of money for these condensing boilers out here doesn't mean that they're going to condense. In fact, if they are not condensing, chances are they're going to be less efficient than any other conventional boiler. So in order to understand the whole efficiency game that people are playing on these boilers, you kind of understand what's happening with combustion first. So I want to kind of talk a little bit about that. You guys are using natural gas here. Do you guys have dual fuel requirements for oil or propane, or do you have other fuel sources? Not on these, but do you have oil on your facility, or do you have propane? Okay. All of these fuels are a hydrocarbon fuel. So meaning you've got some type of carbon and hydrogen, a hydrocarbon mix. When you're using natural gas is not a single compound. Natural gas is something that is created using other compounds. The primary compound in natural gas is CH4. You guys know what CH4 is? No. It's methane. So if you guys have heard of wet natural gas or dry natural gas, it all comes back to the percentage of that fuel that is methane. And here in Utah, who is it that sells the natural gas? Questar, you will not have the same quality natural gas 100% of the time all throughout the year. It will change. I used to do a lot of work up in the northern borders of Alaska. Up in Barrow, Alaska, we sold a bunch of condensing boilers up there. And when it's minus 40 degrees outside, they have to pump a lot of nitrogen into their fuel to get it to move better. And so it will always change. In Springville, Utah, it's not going to be the same as it would be in St. George, Utah, or Salt Lake City, Utah, because of where it's being manufactured. When we say dry natural gas, we're talking a higher percentage of methane is in the mixture. Wet natural gas would be less. The reason I say this is because as it changes, it's going to affect the way combustion is working inside of your boiler. When we started these boilers up, we went in and we calibrated these to the right combustion rate. But that was at the point of what the natural gas was at that time. So as it changes, as the CH4 percentage changes in the fuel, your combustion will change. We don't see a huge change there, but it does affect it. Where we see it being affected more is with the venting, with the piping on the exhaust side because of the air pressures. I'll talk a little bit about that in a second. So when we have CH4 for this process of combustion, first of all, what is combustion? Anybody? No?
Rapid oxidization of fuel.
Okay. We're taking fuel and we want to have a chemical process that occurs with that, some type of chemical reaction, Why? What are we trying to create? Heat. We want to create heat. So we have to, in order to have proper combustion to occur, we have to introduce oxygen. Well, I guess I'm supposed to now, but CH4 plus 2 molecules of oxygen. We need 2 molecules of oxygen for 1 molecule of methane. And that comes back to the whole formula for the process of combustion, which I'll spare you from right now. But this is what we would have. If we get this mixture, do we automatically have combustion? No, I mean, we have this mixture going on all the time. What do we have to introduce in order to get combustion?
Ignition.
Some type of ignition source, right? We have to get this mixture up to its ignition temperature using a hot surface igniter, using a spark, something to get that up to its ignition temperature. Once we do, now we have combustion occurring. Combustion will give us heat. That's what we're trying for. But there's other byproducts of this. What else do we get?
Light.
We get light, okay? What else? Looking at these two, yes, looking at these two compounds that we're using, I've got carbons, I've got hydrogens, and I've got oxygens molecules. So what are we going to create? Well, we're going to create CO2, and we're also going to create H2O. Okay? This is extremely important when we get into the combustion process. When we talk about condensing boilers, this is where it all comes from. Now, again, I've got all sorts of charts we could spend a lot of time on talking about, but when we look at just methane, you've got a high heat value and a low heat value, what we call an HHV and an LHV. The HHV is about 88%. I'm sorry, this is with natural gas, not with methane. So if we look at a typical natural gas, you have about 88%, which is your which is your low heat. Your low heat value makes up 88%, and your high heat value makes up 12%. If we add both of these together, then we have 100% of our fuel capacity. So if I have a boiler that's 100% efficient, I'm using all of the heat for my low heat side and my high heat side. This is with natural gas, which is made up primarily of CH4. This is completely different if you're using propane, or butane, or kerosene, or light oil number 2, because your CH mixture is no longer the same. You don't have the same ratio. So when I have more hydrogens in my hydrocarbon here, if I have more hydrogens, if this ratio between these two increases, what's going to increase in my process of combustion? I'm going to create more water vapor. Okay, now let's talk about water vapor. You guys run steam on your side? Okay, we just got through teaching a 2-day class up at the University of Utah for their technicians on their steam systems. And we just went through all of this. But if I have steam, you guys familiar with steam at all? You guys, okay, let's back up a little bit. What is a BTU?
British thermal unit.
It's a British thermal unit. It's a measurement of heat. How much?
1
Pound of water, 1
BTU
degree.
per pound of water.
Okay, it's the amount of energy it takes to heat 1 pound of water, 1 degree Fahrenheit, right? That's what a BTU is by definition. Okay, so if I have a pound of water inside of a pan, I put that pan on a stove, and water comes into that pan at 60 degrees Fahrenheit, and I heat it up to, let's say we're at sea level, I heat it up to boiling temperature. What is that? 212 degrees. How many BTUs did it take? 152 BTUs if I have 1 pound of water, right? 1 pound of water goes up 1 degree Fahrenheit, so 252 BTUs. My water's boiling. Do I have steam yet?
No.
Okay. I want to turn this 1 pound of water into a gas. I want to change its phase from a gas to a liquid. How many BTUs does it take? Anybody have any ideas?
Changes from blood now?
To change it from a liquid, we're going to change the phase from a liquid to a gas. I'm going to go from water to steam.
170 BTUs.
1 BTU.
From where you're going, you're at 212?
So I'm boiling right now. I've got my pound of water boiling inside this pan, and I want to turn it all into steam. I've got 1 BTU.
970 BTUs.
Exactly. 970 BTUs. Okay, there's a huge difference here. What temperature is my steam?
212.
There's no difference in this temperature versus this temperature. The sensible temperature is exactly the same. But what we've added is a whole lot of latent heat energy. Okay, this is what happens with steam. If I turn my liquid, I heat it up from 60 degrees to 212, very little BTUs, but then it's the change of phase that requires a whole lot of heat energy to do that. Okay, now let's go back to the boiler process. The boiler process, I'm creating a lot of H2O. What temperature am I operating at approximately on your flame? Anybody have any idea what your flame temperatures might be?
1,800.
You can have flame temperatures around 3,000 degrees. In fact, what we try to target when we set up our boilers is around 2,800 degrees Fahrenheit. Does water at atmospheric pressure exist at that temperature? It doesn't. So when I create all this water, all this H2O, what phase what state is it in? It's in a steam, isn't it? So with this chemical reaction that's occurring during the process of combustion, I'm creating H2O. This H2O absorbs my heat energy, this 970 BTUs, it absorbs that heat energy to turn it into a gas. If I do not turn this, if I take this pound of steam and I turn it back into a liquid, I'm going to give up 970 BTUs. So I'm giving up heat energy. If I don't take this water vapor that's in my process of combustion, if I don't take that energy out of it, and all that steam goes up my stack with all my hot food products, I'm not condensing. I've just wasted a measurable amount of energy. So what a condensing boiler is doing, or what any boiler will do, if we start to condense, you're now taking that steam and you're turning it back into a liquid, and as it condenses out, it's giving up a lot of BTUs. So when we look at natural gas, that steam is holding about 12% of our energy because of the H4 is part of that. All these hydrogens are mixing with these oxygen molecules, we're creating H2O, and 12% of our energy is just going up in the steam, with this BTU just locked in and it's going out in the atmosphere. And it's condensing once it gets outside, it's condensing somewhere, but we're not capturing this energy. Okay, so a condensing boiler, with the process of combustion, any boiler, you guys have water tube boilers, right? Don't you have some Bryans? Okay. Have you ever seen those tubes sweat? When you start up the boiler, in the fall when it's cold, do you ever see the condensate form on those boilers? Is it a condensing boiler? No. Have you had to replace your boiler tubes? Have you seen them rust out? Hopefully not.
No.
Okay, that's good. Any boiler will condense. Back in the day, 12 years ago, I used to sell steam boilers in the state of California. We did a lot of food processing plants, paper mills, big industrial facilities. And when I would start these big boilers up, they condense. But it's a non-condensing boiler. Well, why are they condensing? Something's happening. It doesn't matter whether my boiler's allowing it to condense or not. If I'm capturing the energy out of this high heat value, if I'm taking this latent heat energy and I'm condensing that out of my steam, I'll condense. It doesn't matter what kind of material the boiler's made out of. So, let's talk about efficiencies now, real quick. Is this helpful?
That's awesome.
Beneficial to you guys? Okay. Okay. When we look at efficiencies, I don't know about you guys, but a lot of engineers I work with, a lot of owners I work with, they get a lot of salespeople coming in trying to sell them new products. And some of those are people like us who sell boilers. And they'll walk in and they'll say, hey, I've got this new boiler that I want you guys to put in your facility. Look at this efficiency curve. I mean, look, nobody can match my efficiency curve. Do you know who regulates those efficiency curves? Do you know who sets the testing standards for those efficiency curves? You guys heard of ANSI? Did you know ANSI doesn't have a thing to do with setting standards for those efficiency curves? Unfortunately, ANSI tells a manufacturer how to come up with their combustion efficiency. It's one point, it's one value. Combustion efficiency, if I have a boiler, I've got my stack coming off the top of my boiler, I put in my probe here, this is where I'm going to measure it, and all I'm doing with combustion efficiency is I'm measuring how much heat I create. I'm sending in 100%, so my boiler's operating at 100% fire capacity, sending 100% of my fuel. How much of that heat that I create is being used in my process and how much is going up the stack? So what we do is we measure our CO2 and we also measure our stack temperature. Now, I've come up with my stack temperature, but we also have to look at what's our combustion air temperature. So if I'm pulling from the room and my room temperature is 70 degrees Fahrenheit, I would subtract that out of my stack temperature because my boiler didn't create that heat. That was already there. My boiler created the difference. Okay, and what temperature am I coming out at this point? So if we were to take a nomograph for something like this, this would be my CO2 line, and it would be 7%, 8%, 9%. Down across the bottom would be my temperature. So we'd be, maybe 200 degrees, I'm sorry, wrong one, 300 degrees, 200 degrees, and so on. This is my temperature, my net stack temperature and my CO2. And then this line would be my flue loss. Okay, so what we would do is we'd say, okay, I've measured an 8% CO2, and I'm measuring here. We draw a line wherever I cross. That would tell me what my flue loss is. We'd subtract that from 100%, and that would give us our combustion efficiency. Nowhere in here does it say, well, do that at 20% firing rate, do that at 80% firing rate. It's 1 point, and it tells you what your combustion efficiency is. Okay, so AG or the ANSI tells me how to do that. That's fine. Have you heard of thermal efficiency? No? Thermal efficiency is another way that ANSI tells you to test these things. What they'll do there is they'll look at the water coming in and the water leaving, and then they measure the amount of heat that you're adding to that liquid. Okay, so the only difference between combustion efficiency and thermal efficiency is how much of my heat is going through my jacket, how much am I radiating, and how much of that heat is actually going into my water. So thermal efficiency will always be less, but these are giving me 2 points. I'm sure you've seen people's efficiency curves. Look something like this. You guys seen boiler efficiency curves? Never? Okay. I wish I had some to show you, but this is going to be my return water temperature. And this is going to be my percentage of efficiency. Okay, so everybody makes curves like this, guys. This is not Joe Stack just down up here, trying to smoke up your skirt. So we've got 100 degrees, 60 degrees return water temperature, and my efficiency is going to look, with everybody's curve, look something like that. So I can get to 99% efficiency on my boiler when?
Low water rise.
Yeah, my water's got to come back cold enough. My water's got to be coming back around 60, 70 degrees Fahrenheit. Do you ever see that in a boiler system? It'd be nice if we could. If you do snow melt, you can have temperatures that are around 90 degrees, 100 degrees, so you're going to be somewhat efficient. When I got to Boise, almost every job, this is why I asked the engineers this question, almost every job that they were putting these boilers in, they were coming back with 160, and they're heating the water up to 180. Their boilers were operating at 83 to 84% efficient at best, just like any other boiler would, because it goes back to the whole process of combustion. It doesn't matter. So why? Why am I more efficient with colder water?
More latent, it's absorbed out of the steam.
Okay, there's more. Think about your hot flue gases. They're always going to be the same temperature. They start at around 3,000 degrees, and then you've got your water. The greater the difference, and this happens with anything with heat transfer, the greater the difference between my two mediums, the more heat transfer, the more heat will pass to the colder medium. If that gap becomes closer and closer, the gap shrinks, I don't transfer as much heat anymore. It makes sense. So if I have boiling water over here, you will never have a steam boiler that can be greater than 82, 83% efficient. It's impossible. You can't. You can't pull enough. Remember, combustion efficiency, we're measuring how much heat went out my stack. If my water is boiling at 212 degrees, can I send my flue gases out at 105 degrees? I can't pull heat and just stick it anywhere. I mean, my water's got to be heated up, and once it's heated up, my flue gas can't continue to cool. That's fundamentally impossible. So what's happening is the colder I make my water, the more heat I can soak up from my flue gases. So that's our #1 goal with trying to create high efficient boilers. But this is what most everybody does. So it's going to be your task, again, I don't know everything about your system out here, but it's going to be your task to try to get your boiler heating system, if you want high efficiency, to get your boiler heating system to operate as cold as you possibly can. It goes against everything you've ever thought about boilers and boiler systems. Because if I'm operating here, I might as well have just spent money on a non-condensing boiler. And you've spent a whole lot more money for these boilers than you would have a non-condensing boiler, and those boilers, might even be more efficient. You know why? What gives your boiler the permission to condense? Why is this boiler a condensing boiler, but yet a big old Cleaver Brooks fire tube boiler is not a condensing boiler? I used to condense on them all the time, but it's not. These are. What's the difference?
That's heat exchanger.
Maybe one less heat exchanger. This one does have 2 heat exchangers, but there's something about the heat exchanger. This water vapor, the H2O that we create, if we have a steam system, water is not corrosive, right? Water is pretty basic. It's on the pH chart. Let's draw a pH graph here. We go from 1 to 14. What is base? Or I'm sorry, what is the neutral? 7. Acid is going to be 13. Acid's going to be over here. So this is going to be your acid, this is going to be your base, or a higher alkalinity. Okay. Coke. Everybody like Coke or Pepsi? You know what pH you drink? You know what pH that stuff is?
Acid.
It's an acid. Do you know where it sits on the scale?
3.
2. Have you ever put a nail in Coke and leave it overnight? Leave it for a couple of days? What happens to the nail? My daughter did this for a science project. It's gone. After a couple of days, it's gone. Okay, that nail, all those, the metal in that nail, all the iron, it's gone. It's eaten away. Okay, because of the acid. All this water vapor that we create, normally water vapor wouldn't be corrosive, but we have a lot of carbon in here, so we're forming a carbonic acid. So as we form this condensate, first of all, in the first pass, comes out at about 5. You're already an acid. So if you put this on cast iron, you put this on copper, you put this on steel, it will eat through that metal. I've seen copper tube boilers fail within 2 months, okay, because copper is very thin. I've seen cast iron sectionals that are 1/4 inch thick last 30 years, but you open those boilers up and they've been condensing and there's very little left. It's all rusted out the boiler. Okay. You can get cycles of concentration because with typical boilers, old school boilers, you're creating water vapor. It cools off because you've got a cold heat exchanger inside. My flue gases, that they travel up, we start to condense towards the top. Where does the water droplets, where do they go? Back down the hot zone. So what happens to them? They re-evaporate. So we get a cycle of concentration that occurs, and that drives my acid level down to 3. That'll eat through the metal even faster. Okay, so we try to prevent that. So all of your new boiler designs, you'll notice that your burners are usually towards the top, and the flue gases pass down, and vents are kind of coming out the back or the bottom to prevent the cycles of concentration. So when the water droplets form, they drip down to the cold zone, and then you drain them out of the boiler and get them out of there. Okay, and that's what this boiler is doing. When you look at this boiler, and we'll go over a little bit, it goes down the primary heat exchanger, back down the fire tubes, and then it drops down to the condensing chamber, which goes out, which the condensing chamber is different than a normal boiler. So again, I go back. What's different between a non-condensing and a condensing boiler? Okay. Yes, but it all comes back to the construction of that condensing chamber, or the construction of the heat exchanger. The heat exchanger, the metal that you use, has to resist the acid. So you have to have a boiler that gives you the permission to condense, or that will withstand the corrosion that's going to occur from the acid. So the boiler heat exchanger is made out of what? Stainless steel. Or you get some aluminum boilers. Or you can epoxy coat heat exchangers. They've got a hybrid design. You have to design that boiler so that this acid is not going to kill that boiler and eat through that boiler. And hopefully the boiler will last at least 20 to 30 years. And that's our end goal, right? We just did a job up in Boise where they were replacing the boilers after 5 years. And the guys were like, yeah, these boilers have been around forever. They're a good old boiler. Well, how long have they been? About 5 years. Okay, wow, you've got 8 2 million B2 boilers sitting here and replacing all 8 of them after 5 years because they didn't have the permission to condense. So we're putting condensing boilers in there, and these boilers will give them 20, 30 years. And they're thrilled. Okay, so that's the difference between a condensing boiler and a non-condensing boiler. Because a condensing boiler gives you the permission to condense because the metal will resist the corrosion somehow. So when we look at this boiler, these Fulton boilers that you have, they use, you can tell I'm not a real great artist up here, but try to draw what it does. The flame, you'll notice when you look at the boiler that the burner is up towards the top. That burner shoots down a primary tube. Once it hits the end of this tube, it comes back in what we call tailpipes. These tailpipes run back to the front of the boiler. And so again, my flame temperature starts out around 2,800 degrees Fahrenheit. So we're really hot. Okay, this is what we try to target. Really hot flame. By the time it hits the end of these tubes, we're no longer a flame, we're just hot flue gases. So we're 300, 400, 500 degrees Fahrenheit. We hit the end of these tubes, we come back, we're still very hot. You will not start to condense that water vapor in here until 128 degrees. And I wish we had time so I could explain that to you. But once my flue products reach 128 degrees Fahrenheit, that is the dew point temperature of all of my water vapor. So just like the clouds outside, once you reach the dew point temperature of your air and water mixture, then all of that gas, the steam, will rain out. And as it does, it gives up all of that heat energy. So we're giving that heat energy up so that it can get back into the metal and back into our water. But it doesn't happen until 128 degrees. That's not occurring up here. So then we drop it down and we run it through another heat exchanger. This is kind of like a shell and tube bundle, a straight through shell and tube bundle. And this up here is made out of a heavy grade carbon steel. This down here is made out of duplex stainless steel. Some of the heaviest grade stainless that you can get. Okay? This is where we're going to condense. This is where we're capturing the rest of that 12% heat energy. Remember, before we condense, we can get 88% of our natural gas mixture, the heat energy out of it. But if we want to be 100% efficient, then we have to capture the last 12% of my high heat value. So in order to pull that out, that's what we're doing down here. You guys ever used economizers, stack economizers, where you grab the residual heat off of your flue that leaves the boiler? No? This is really, it's just another economizer, but it's a great big stainless, duplex stainless steel bundle in there that's grabbing that heat. Okay. So you've got two heat exchangers in this boiler, but it's acting as one heat exchanger process for what's occurring. And then the flue comes off the back, we take the vent off the back, but now here's where all of our water vapor is forming. So we pitch this heat exchanger slightly, so the water vapor the water vapor condenses. Water vapor condenses and it will drain out towards the back of the boiler. And if you've been around the back side of these boilers, you'll see some hoses that come out the back. Also, coming off the T here, we've got a drain T, and that's coming over. We're running the condensate that's forming because we're raining inside this stack. We've got acid rain in here, which is why your stack has to be constructed out of AL294C per code. So this is a very high grade of stainless. So it's raining acid in here. We try to collect all this acid into one point, and then we bring it over to the drain and we send it out. Can you send that down the drain the way it is? That acid? Everybody does.
No.
Not for long. Yeah. There's only been, in all the states that I've taught these classes, there's only been really two states, in Texas and San Francisco actually. The San Francisco jurisdiction does not allow you to do this. They state that back on this pH scale, you have to be at least 6.5 pH to send it down the drain. Well, we're already at 5, so you're violating code. So what? What's going to happen?
Keeps the pipes clean.
Keeps the pipes clean. What are your drain lines constructed out of?
Cast iron.
Cast iron. And over time, depending on how often you condense, if your water's coming back at 160 and you're heating it up to 180, will you ever condense? Again, my flue gas has to get to 128 degrees Fahrenheit. So if my water coming back to my boiler is 160 and I heat it up to 180, will I ever get my flue gases this cold? You can't. That's why my boiler really can't get into this efficiency until my water temperatures get less than what?
128.
Less than 128. That's why these brine boilers that you've got, I bet you if you go back and read their warranty, they state if you operate our boiler less than what temperature? Anybody know?
160.
It's actually 140. With these boilers, if you bring back colder water than 140, you violate their warranty. They're trying to give you a buffer, a pillow, a cushion so that you don't ever hit this. Because you will kill those boilers. You will rot out all those tubes from the outside from all of that acid. So again, they're trying to prevent that. So our goal is to get our water to come back to these boilers colder than 128 degrees. If you don't, you wasted your money on a condensing boiler. Okay? Yeah, I don't know your system well enough, but any system we can make do this. Your system was designed, your heating system was designed for the coldest day of the year. How often does that occur, percentage-wise?
Not this year.
Not this year, it's not going to happen, right? Okay? On an average, you might get it 2% of the year. You'll be at the coldest temperature outside. And then you're going to have all of your control valves open 100%. You're going to be putting as much heat in the building as you can. And maybe they sized your building for 180 degrees supply temperature on that coldest day of the year. But the whole rest of the year, I mean, heck, today we probably need heat. But today, I guess today's a little colder, but yesterday it was 45 degrees, 50 degrees. We still need heat, but do I need 180 degree water?
Well, this plant's a little bit unique because we don't run it more than 150.
So your return water temperatures are coming back
90.
perfect. Yeah. Perfect, which is why you've got the condensing boilers in here. Resetting our water temperatures is big. Resizing heat exchangers, coils, whatever, for colder. I've got an engineer I work with out of Indianapolis. 100% of his job, their design temperature is 0 degrees. So the coldest day of the year is 0 degrees. And every school that he does, on the coldest day of the year, he supplies 130 degrees Fahrenheit. So he's always condensing, even when it's really cold outside. So this is what we teach engineers. You've got to be aware of this. But you now, as the operators, you've got to be aware of this so that you keep your water as cold as you can. So what we tell people with the reset is reset it back, and if you start to get some complaints, it takes a little too long to get the room hot, well, then jack the temperature up a little bit. But the colder you can keep it, the more money you're going to be saving on your operational costs. And again, this isn't my boiler talking. This isn't my competitor's boiler talking. This is everybody, because this all comes back to the process of combustion. Okay, it's not magic. It's not something that anybody's making up. Okay. Questions or comments on anything we've talked about? No?
Yeah. So what do you do with the water, or the
With the acid?
drain? Yeah.
Okay. So somehow you've got to take this 3 or this 5 and get it back up to 6.5. Again, if you don't, the more condensate that you have, where you guys are coming back with 90 degree water, potentially you're going to have, if you go back there and look, you'll see like a hose being left on, just water continually draining out. Okay? That's an acid draining out. That will eat through your cast iron drain lines. That will, if you have plastic drain lines in your building, well, you might be okay, but once it hits the city lines, so who's going to pay to repair that city drain line once it gets eaten out 10 years from now? That's the problem it's coming back to. Who's going to pay to replace all of your building drain lines because it wasn't treated properly? So that's what everything now is coming back to. Condensing boilers, it came out around the, predominantly more around the late 80s, early 90s. So we're now getting to a point where we're now starting to see buildings fail. Who's going to pay for this? So we as manufacturers, we recommend, hey, this should be neutralized somehow. We've got to get it back up to a neutral level so that it's not going to eat through this material. So somehow we've got to do that. The easiest way is to run it across line deposit. And that's what we've given you on your boiler. What did we do? Did we do the little buckets, or did we do the little trap? Okay, so you guys have buckets that they can put the lime deposits in. Okay, so as we come off the boiler, well, I need to talk about that too. As we come off the back of the boiler, again, you've got your stack that takes off. We're bringing our acid out here. We're bringing our acid out of the back of the boiler. And if you look at the back of our boilers, we run through one little bucket first. That bucket is not to neutralize it. Again, what's happening is we had to create an opening at the bottom of this boiler so that we could get the condensate out. The flue gases, because they're hot, they're lighter than air, so they're going to go up the stack, and through chimney effect, they're going to go up out of the atmosphere. But unfortunately, the water, the steam was also going up, or would go up, but it's not anymore because it's now turned heavy. It's turned into a liquid. So it's coming back down. So we have to basically punch a hole in everything, and we now have to run that to the drain. By doing that, what are we now blowing into the room? Yeah, we're blowing products of combustion in the room, potentially killing somebody. So to protect us, to protect you guys, we have this little condensate trap. All this liquid goes through this condensate trap. It's got a little float level in there. That float will detect the level of the water. If the water, say you shut the boilers down for the summer, that water will start to evaporate and start to go away, and so the float drops. Eventually, without that float inside, you have no water when you turn the boilers on until you start building up condensate. You're going to be blowing products of combustion in the room. Why would the products of combustion want to go all the way up the stack when some of it could just be dumping into the room? It's very dangerous. So this trap, this level, will detect if water starts to leak out. It will drop. We've got it tied into the city line so that we'll fill it back up with city water to always keep some type of prime on that little trap that we created. From here, we now take it over to another bucket that fills up with the liquid, and then we drain it off down over to your city drain. This should be filled with lime rock deposit. That lime rock deposit will neutralize this. The typical sizing for this, to get your pH to go from 5 up to 6.5, needs to have about a 30-minute contact time. So as long as you've got good lime rock deposits, 30 minutes on that lime rock will give you that neutralization that you need. If you're at 3, then you're going to need about an hour and 30 minutes contact time. So that's usually how we size this based on the boiler. So you should have a basin that's large enough, but if not, if over time you realize, hey, we're pushing more condensate through here than we normally would, you might not be getting the neutralization that you want, so you better put in a little larger basin. Also, you need to check this lime rock deposit every 6 months. You need to check the liquid that's in here, check the pH level of it. If this pH level, every 6 months, so what will happen, I've got into systems that have been installed for a year or two, and there's nothing but sludge in here. The rock is gone, it's just kind of a mud or silt. There's no neutralization occurring now. Make sure you check this pH and add new lime rock deposits so that you're getting that the neutralization to occur, otherwise you will leak out your building drain lines. Okay. Just to give you an idea of how much water vapor we create with natural gas. Anybody want to guess? You've got, let's see, your boilers are 4 million? Okay. So you've got 4 million B2 boilers. So we've got 16 million BTUs out there that could potentially be running. Per 100,000 BTUs, you form about 1.15 gallons per hour of water vapor. So if we multiply this by what, 16? So you're going to be close to 20, is that right, times 16? No, because that's 16 million.
Yeah, 16 million.
That's 160. So you're going to be going about 170 gallons per hour, potentially, of condensate flowing out of those things. Now, to do that, you're going to have to be 60-degree water. Your boilers are going to really be chugging with really, really cold water, so you're not going to get that much. But that's what you're going to want to watch. So, and again, that's going to be on the coldest day of the year. Coldest day of the year, your water temperatures might be a little warmer, so you're not condensing as much. So it kind of works in your favor. But that just gives you an idea of how much condensate or how much water vapor is forming. And if you condense 100% of that, that's a lot of water. It's a lot of acid. Okay. That's one of the biggest problems, one of the biggest issues that we see with condensing boilers is lack of maintenance. Unfortunately, condensing boilers will require more maintenance because it's a dirtier environment. It's not the boiler's fault, it's the application. Every time you get water forming inside, you now start to form rust, you start to form minerals, particulates, whatever, and it starts to block passageways inside of your heat exchanger. It starts to eat up your heat exchanger, and that will quickly kill your boiler. So you need to make sure that you're doing the regular maintenance that we're going to go over here. Any other questions on this before we start getting more to the technical side of the boilers? No? Okay. I brought 5 O&M manuals. I know we don't have to provide them here, but I wanted you guys to have stuff to refer to. So maybe group together as best you can, share a couple of manuals or a couple of guys to a manual. case of an emergency, you guys, again, I'm not the controls guy, but I'm sure per code you've got an emergency stop switch out there in the mechanical room. Do you know what door that's by? Both doors? Okay, so in case of emergency, hit the switch and run. Best thing you can do, by hitting that E-stop switch, you guys know that that kills the power to the boilers and the boilers no longer fire. If you're with the boilers and you need to shut them off, simply, I believe, yeah, I work on so many boilers, don't these boilers have an on-off switch on the front of them? You can just take the local switch right on the boiler and turn it to off. I think it's an off and a remote. So when it's to remote, it's being controlled by the control panel. When it's off, it won't receive any signal. So if you need to shut a boiler down, just kick it to off. It's going to shut everything down on that particular boiler. If you need to shut the whole plant down right now, hit that E-stop switch and everything will be fine.
Those tied into our existing switch that we have.
Two new switches.
There's two new ones.
On each door.
Yeah, per code, the boilers in that room have to be controlled by switches in that room. And so I'm sure your other boilers have their own E-stop switches on those doors. So as you exit, in case of an emergency, as you exit the door, you hit that switch, just push the switch in and you run. So depending on how scary it is, you might want to run a little faster. Okay. If these boilers operate outside of their normal operating range, again, we've set some of the operating range up, that we'll go over some of that. But if they start to operate outside of their normal operating range, one of the fastest things that you'll see, and we go over this in the actual maintenance of this thing, is you'll see the flame color change. We've set this, again, going back to what we just talked about. Again, this is important groundwork to this whole training. To get the proper combustion that we've talked about, to get that CH4 and the 2 molecules of oxygen, requires some tuning on our part when we start these things up. We have to make sure that we have enough excess air, we have enough oxygen molecules for this whole process of combustion to occur. What we do is we dial that into about an 8% CO2, which gives us about 10% excess air using the natural gas we have here. What that means is we've dialed in this proper air to fuel ratio, so every 1 volume of gas, we've got 10 volumes of air, is typically what that works out to be. Okay. Now, if that were to change, then your flame is going to change. I mean, just go back to some real elementary stuff. You have a candle burning and you put a cup over the candle, what happens to the flame? Why? There's no oxygen, it runs out of oxygen. It burns up the oxygen inside and then it runs out. Before it burns out, what does the flame start to do? Starts to what? Smoke? It gets smaller, it changes color. You might get more smoke off of that. Okay, that's exactly what's going to happen inside your boiler. If it starts to be starved of oxygen, it starts to run too rich, then you're going to start to smoke. Well, what do we start to see inside of the boiler before we form? Soot. You'll start to see a lot of soot buildup. Soot buildup is bad because that instantly changes your heat transfer. It's like putting a nice blanket over your heat exchanger. It limits your heat transfer, and the whole process of combustion just completely goes. So as soon as you build up soot, it's going to start building up faster and faster and worse and worse. So you've got to watch that. On a lot of burners, not this one, but on maybe on some of your other boilers, you can see soot when you look down the viewport, and you'll see glowing embers inside. Glowing embers, you know, just like in a fire, it's the soot buildup. Soot is unused carbon. Okay, there's not enough oxygen to burn up all that carbon. You'll start to run smoky. Are you signaling me?
Just when I get close to the end of the tape,
Okay.
I'll go 5, and then I'll go 2, 1, and then talk real fast. Just try to find somewhere to stop.
Where I can stop. Okay.
Yeah, no
And did you
communication.
just give me a 2 or a?
I'll give you 2 and then a 1.
Did you just give me a signal?
No.
Okay.
I'm just letting you know. I'm getting down there.
Okay. Do I only get 1 tape? Then we're done. We're good.
Yeah, that's it.
I can leave.
No. I splurged and bought another one.
Okay. What were we talking about? Carbon. The carbon and the soot. So you've got to make sure to check that and check the flame, the quality of your flame. When we get into the daily maintenance, that is something that you should be looking at every day. Now I don't think your boilers are going to be operating every day, but when they are operating, make sure that you look down there and you just check that flame quality every day. It'll tell you what the flame should look like. Okay, that becomes very important because as you start to get outside of these normal operating windows, which happens, you know, the way these things are vented, these new high efficient boilers are so temperamental. What happens? My stack is coming out. Your vent is going off the roof, right? Where are you guys pulling your combustion air in from? Sidewall? Okay, good. I mean, not good, but that's a perfect example of what's going to happen. The wind starts blowing against that wall where that vent is pulling the combustion air in, what happens? Is your combustion going to change? You betcha. Because we just changed the air pressure. We might now be having too much air through the process of combustion. So we're going to run lean. Okay? As we run lean, what's the dangers of running lean? I didn't really go over this, but we're trying to shoot for about 2,800 degrees Fahrenheit. Okay? And then the reason we want this, our flame temperatures could be around 3,200 degrees, 3,400 degrees Fahrenheit. The hotter the flame temperature, again, the bigger that gap between my water temperature and my flame, so I have more heat transfer available. But I've got to cool my flame temperatures down so I prevent pollutants. Okay? Because most of the air that we breathe, 79 or 78% of the air we breathe is what? Nitrogen, not oxygen. We don't need nitrogen for combustion. We need oxygen. So we're putting all this air in for the process of combustion, but we're feeding a lot of nitrogen. With extremely hot flame temperatures, if I exceed 2,800 degrees, something's going to happen with that nitrogen and the oxygen, that O2 that we've got in there and the nitrogen. You guys ever heard of NOx? Okay. NOx, N-O-X. NOx is not one compound. The reason it's an X is the X is a variable from 1 to 7. The EPA regulates nitrogen dioxide, NO2. So if I have very hot flame temperatures in excess of 2,800 degrees, we force a chemical reaction between the oxygen and the nitrogen, creating more NOx. So we can't do that, so we have to subcool our temperatures. So I add more oxygen, I add more air, that excess air I mentioned, that 10-to-1 ratio. I add more air to cool my flame temperatures to prevent my pollutants. Okay, that's good, but I just decreased that limit, or that difference between my hot flame and my water. I made it smaller, so I'm less efficient. So, if I start to run lean, because the wind's blowing, my efficiency goes down. So these are things, again, simple little things that will change. That's why it's going to become extremely important when we go over the maintenance requirements. You're going to notice in there, it keeps saying, check for blockage in the flue. Because any air restriction, anything that's going to restrict the amount of air that's coming into here is going to change your combustion rate. If it's blocked, you're going to start running rich. You're not going to have enough oxygen, just like that candle. You're going to start to build up soot. You're going to crud up your boiler. You're going to put a whole lot of pollutants out. It's not good. It's going to kill your boiler really fast.
What if the fan on the flue regulate how much outside air is coming in, or is it just has nothing to do with that?
The fan that you've got here on these boilers is at constant speed. So what you've got on this boiler is we dialed it on at high fire. So okay, we want 8% CO2, which means I need so much excess in that 10-to-1. So 10 volumes of air for 1 volume of gas. So I set that up at high fire. Then we set that up at low fire. So when this thing modulates all the way down, these boilers have a 5-to-1 turn-down ratio. So they'll operate at 100% down to 20% and any infinite point between these two values. So I set it up at high fire, I set it up at low fire so that we have that right combustion. But then this boiler also gives you 8 other points between there, in staged points where you can go in and just make sure, as you tune it up, that each stage through that modulation range. And what it's doing is you've got a gas valve, not the gas valve itself, but you've got what they call a gas serve valve and an air serve valve. And as we set this up electronically, it sends out a 4 to 20 milliamp signal to both of these valves so they modulate together. So we're limiting the amount of air. The fan's still the same speed, but we're limiting the amount of the oxygen that's coming in through this air serve valve, and same thing with the gas. So we're maintaining that same 10-to-1 ratio from high fire all the way down to low fire. Does that answer your question?
I think so. Okay. But what if that outside air damper,
Okay.
if it is blowing directly into the vent, won't that adjust?
And see, no, it won't, because what we've set it up to is just it's a position.
They're
So
both
we're
tied
setting
into the exact same.
It's the same controller, but it's sending 420 milliamp signal not based on the O2 that it's reading or the oxygen that it's reading. It's sending a signal based on the position where the valve needs to sit. So as we program it, at low fire it needs to be at maybe 10% open. At high fire it needs to be at 98% open.
So you might get more air with more pressure.
Yes, you will get more air with more pressure. There are ways around it, and in the industrial side of the field, we see it all the time, where they'll have O2 sensors. That if I have too much O2, then close my damper. If I don't have enough O2, open my damper. But that becomes extremely expensive and very tough to maintain. And so commercial boiler manufacturers, they'd never sell a boiler, first of all, because it's too expensive. Second of all, the cost to maintain that is extremely expensive. So it's not and it's not an option on the commercial side. But yeah, it's good that you picked up on it, because that's exactly what should be happening. Okay. Okay. For those who have a book here, let's start going through some of this book. I want to get through some of this stuff here. What time do we have? Okay. Oh, that's right, we started later. I'm supposed to start right now. Good, you got me till 3:30. We got lots of time.
We're moving everything.
How long do I have? What time do I have to quit?
Same amount of time that was in there. It was an hour and a half or 2 hours. What was it? Hour and a half.
And we started at 1.
Yeah.
So we've got a half hour. Okay. I'd like to get you guys out there. Do you want to get your hands on the boiler and
Definitely.
do some of that? Okay. So we better go through some of this pretty quick. I'm not going to take you through all of the startup procedures then on what we do to start it up. You guys, again, it's all detailed inside this book. You open up the book, they've got some full guide up front here, but in the operation, in the operation they've got to perform pre-startup inspection and then commissioning the boiler. Commissioning of the boiler is what we do when we start the boiler up, so that we fine-tune that combustion, we get that at its peak performance level that we want it to get to. You guys should be doing that at least once a year. Okay, these things are not like an old school boiler that's operating 80% efficiency or less. You've got to make sure that that combustion rate that we just talked about is maintained, and you have to check that once a year. Do you guys have your own flue gas analyzer?
Yeah.
Do you know how to use it? If you
We
want,
know how to use it. I don't know how quality it is.
if you want, again, I've offered all sorts of free training to you guys. I'll gladly come down, we'll feed you lunch, and I'll teach you how to use a flue gas analyzer. Because it's something that you guys need to know how to use. You need to be able to check the combustion rate on this. If you want us to come down, we'll be more than happy to check it for you too. It's very simple, but you got to make sure that that CO2 and the O2 is held at a constant rate, because that will change over the years. You've got to, because the boiler will foul up, it will start to derate itself, and so you've got to make sure that you're compensating for that. But we won't go over all the details here, because unless you know how to use the flue gas analyzer, you don't really know what to watch and what to do that. Do you hire that out right now, or do you just not do it on your existing boilers? Yeah, and again, these boilers are how old? I mean, your boilers now are, any ideas?
10 years.
Okay, so they've been in a while. 10 years ago, they still made some pretty good boilers. Up at the University of Utah, we've got some boilers there that are really old we're working with, so it's a lot of fun.
And we do get them checked.
Yeah, I'm sure you got to be hiring somebody to come in and have you check them out.
Yeah.
Okay, but again, these things are not as forgiving. Any high efficiency product is not as forgiving as just the old standard atmospheric or forced draft type appliance. This gets a little bit more temperamental. And as long as you follow the schedule that they give you, then everything will be fine. Just, it's important that you follow the schedule. Okay, so we won't talk about the startup instructions. As far as making adjustments, this thing is nice. It's got a little Siemens LM37 controller that's up front. You get into this thing and you enter your code. The code for now, you guys can get in and reprogram the code. I don't recommend you do that, because then it makes it so somebody might lose it. But in here, it does have a default code to get into these things of 5 A's. So once you get into the password area, you enter 5 A's, hit enter, and then it lets you into the back end of the code. And then you can get into, as the boiler's firing, the 10 points, low fire to high fire, and the 8 points in between on where you can set up your combustion and make the adjustments that you need. So as you're standing there watching the boiler operate, you look down that viewport. As you watch the boiler operator modulate, if during that modulation range the flame looks any different than it's supposed to look, then that's when you know what, we better get in and we better check all of this. And as you do that, as you program these different percentages for the air serve valve and the gas serve valve, you're changing the position on these valves, and you actually see them change as you increase or decrease the numbers. And so you're programming that in. It's all very simple. There's instructions in here on how to do that. And like I say, we're just up here in Salt Lake. If you guys have any issues, you can call us and we can walk you through any of that. But the adjustments, it's not going to be something you're going to need to be making every week, every month, unless you see a problem. But it should be something that you're checking at least, with this combustion analyzer once a year. Troubleshooting. One of the things they wanted us to talk about were some typical problems that we see with these boilers. again, I'll stress, the most typical problem we see is poor combustion. So that's why in this manual, in the maintenance instructions, it's going to keep repeating over and over, check for blockage in the flue. Make sure there's nothing obstructing the combustion air inlet and the exhaust leaving the building. Simple bird's nest, in the combustion, I see that all the time. Some type of nesting that gets put in there. So these are things you want to watch out for. There is a troubleshooting section in 4.7 that becomes very, very handy. I've highlighted a few of these that I wanted to go over, but we don't have time. In the maintenance, back here on 4.7, section 4, page 7, it says problem. What's your problem? So if you have my fan won't start, then it gives you maybe 8 different things to check. It could be this. It could be that my high temperature is tripped. I see that quite often. My boiler has a call for heat, but my fan's not turning on. That if your high temperature, your high limit controller is tripped, then that's locking everything out. So you'll want to check that to make sure that you know what your high temperature limit control has a little red button on it. Push the little red button and see if that trips it. Make sure that the temperature on the boiler is not exceeding what that high temperature limit is set to. You might need to make some adjustments. Another big one that we see, because of the CSD1 gas codes that are here in Utah, we require a low gas pressure switch and a high gas pressure switch. It may be that, typically we see that the low gas pressure switch is out. If it's a low gas pressure switch, what's probably happened is you had a spike in your gas pressure because everything came on at the same time, your gas pressure dropped, and it tripped your low gas pressure switch. So if your fan's not starting, again, that's something you might want to check out too. Your pilot fails. We see a lot of ignition failures. We see a lot of flame detection is defective. This is where you're going to start getting into parts replacement because these little, UV sensor is gone out. Or we just had a job the other day where we had to replace the UV sensor. The nice thing about this boiler is it's not using, it's going to be like your brines that you have. It's not like some of these other condensing boilers that use residential type stuff. You don't have a hot surface igniter. You've got a nice industrial spark igniter. You've got a Honeywell arm. No, you don't have that on this boiler. You've got a Siemens LM37 controller. It's some pretty heavy grade stuff that you've got, stuff that they're messing around with. So again, that troubleshooting section is pretty good to refer to. And then as far as the maintenance, let's go over the maintenance here. Turn to 4.2. This is where you probably want to, your boilers came with a O&M manual with them. Each boiler had one. I would copy that. I would do something with this next section I'm going to go over and pin that on the side of your boiler, pin that up here on a wall, something where you know this is what I've got to do and this is when I've got to do it. Okay? So if you go to 4.2, it breaks it down by day, by week, by month, by every year. Okay? All right, so first of all, daily maintenance schedule. Again, they want you to inspect this thing daily, but just make sure that the temperature and the general conditions around the boiler are fine. Make sure that the flow of the combustion, again, daily combustion ventilating air, the boiler's not obstructed, check for any obstruction. And then the last, make sure that all the combusto or the clearance area around the boiler is free of combustibles, just safety-wise. On a weekly, you want to make sure that again, weekly, look in and make sure the flame, this is where it gets important. A normal high fire flame shows an orange screen with a blue halo. That's what you should see. In low fire, the burner should display a reddish orange glow. If you ever see the flame leaping, what is that a sign of?
High pressure air.
Too much air, too much oxygen in there. And it'll be very brilliantly orange type look. I'm sorry, or yellow, very yellowish. If it's not enough oxygen, the flame might be kind of lagging and it will be kind of a deep orangish look, and it just not a brilliant orange, kind of a dirty orange look. And those are the signs you want to avoid. If you look in and you see that, again, check it weekly. Make sure that it looks good. In low fire, the burner should display a reddish orange glow. Correct air adjustment is essential for the efficiency operation of this boiler. If an adjustment to the combustion is necessary, the flue gas composition. So again, don't think you look down there and you see the flame and it's a bad color. Don't just, okay, well, I'm going to get in and change my positions on my valves. Don't do that. You got to plug in your flue gas analyzer first, find out where your CO2 is, and then dial that CO2 level into where it needs to be. Okay, so it's not just a visual test and okay, well, I'll make some adjustments. I mean, the numbers, the percentages that you go are very small and very minute, and it can change very quickly depending on what fire rate you're operating at, okay? All right, monthly. Monthly inspections should include the following. Test the high limit control. Again, you want to make sure that your high limits aren't going to fail. You guys have seen the results of boilers exploding before? That's pretty simple. On our boiler class that we teach, we've got some pictures of these boilers at Mary's Hospital that was back east. The boilers, big boiler lifted up, went outside the building, and was resting in the parking lot. And the boiler door that it blew off, there was a man ladder, luckily not a man, but a man ladder in front of it. It was permanently encased in that boiler door that was 2 buildings away. So when a boiler blows, if the high limit, problem with the high limit is that water will start to boil potentially, and if it starts to boil, and you start to build up pressure. You guys fans of Mythbusters? Have you ever seen the water heater one out on the tarmac where they take that up and it gets to about 362 psi before it blows, and they've got that little red house built to California code standards, and the water heater's in slow motion. Oh my gosh! It takes off through the roof, goes up, and it goes so high you can't even see it, and it comes back down almost exactly where it took off from. They said that was not a bomb; it was a rocket, and really that's what it is. As the house fell down, the windows were still intact. So you don't want that to happen, so you've got to make sure that your safeties are working. So it gives you instructions on how to test your limit controls. Again, check your flue gas temperature at the outlet. Your flue gas, did you guys have a way to do that? If you can, it's not a bad idea to do, is install a little thermometer, some type of temperature gauge to look at your flue gas temperatures immediately leaving the boiler. If you see a drastic change in that, that's an instant sign that soot is building up in the boiler. If that temperature starts to go up, you're building up soot. Okay? So that's a good way to do that. So they're saying monthly you want to check that temperature. The probable cause is soot or water scale buildup on the tubes. You're not pulling enough heat off of the flue products, and so that heat's now leaving the boiler. So you have an insulation blanket either on the hot side, the fire side, or on the water side. Something's going wrong. And they say, as soon as that happens, contact us. Don't, well, we'll just leave it be and everything's fine. Something's got to be done. Okay? Test the low gas pressure switch every month and the high gas pressure switch. Make sure that they're operating. And then you don't have the low emissions model, so you don't have to worry about the next portion. The annual maintenance and inspection schedule. So annually, check the fuel train, the burner, and the control panel to make sure all the components are free of debris, free of dust, free of any sediment buildup. Examine the venting system. Again, there it is, the air intake and exhaust piping. Make sure this is a pressure-powered boiler or a positive pressure boiler, so your stack is airtight. Not only is it watertight to prevent all that condensate from leaking out, but even though it's this AL294C, which is some of the highest grade stainless you can get, I have seen where condensate builds up. If you ever have your flue start to sag, your condensate will build up in there and it will eat through this. And I've seen that happen up at many jobs where the condensate isn't drained out properly and it will eat through the metal. And as soon as you do, because it's positive pressure, you'll now blow products of combustion into the room. It's not good. So always, annually, check your flue. Make sure there's no sagging, there's no deformation in this thing. Make sure that it's airtight. That check all of your seals, your joints. Make sure that they're sealed properly. You're not getting blow through on there. So that's what they're saying here. Check all joints, check piping for corrosion, check that the piping is clear of debris, check that the condensate drain is still functioning. Make sure that that condensate drain isn't getting plugged. So on your drain tees coming off the back of your boiler, back of your flue, make sure that those drain tees are still free and clear so that the condensate, the acid's getting out. Inspect the hydronic heating system for other problems, perform combustion analysis. Okay, so that's what we're talking about here. Perform combustion analysis and adjust it if necessary. Leak test all of your gas valves and test your pressure relief valve per the manufacturer's instructions, and they tell you how to do that. For 5 seconds, line the valve to snap shut. Pretty simple, right? You guys nervous? Have I scared you a little bit? You know what? And I'll be honest with you, no matter how much we stand up here and say maintenance, 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 half the jobs we do this on, they never maintain. And I mean, the boilers, we might get a call 5-6 years from now, and hey, the boiler's chugging out, it's tripping out on flame failure. So we go out and, yeah, it's got soot in it, so the boiler requires some cleaning. But usually it's not detrimental on the boiler. But I don't want to say that, well, I guess it's not on camera. But again, we strongly recommend, we strongly encourage you to make sure that you follow this maintenance schedule to the best that you can to make sure that this thing keeps its peak performance. Again, you spend a lot of money for a condensing boiler. You'd like to see a return on that investment. That's why it's here. You're not going to get a return on that investment if this thing now starts to operate as efficient as your old ones were or worse. So the whole key to that is make sure that you keep it maintained. Okay? Any questions? I'm done in here. We got a little couple minutes to go out and take a look and look around the boiler. You guys had a chance to play with the boilers at all? Have you fired them at all since we had them fired?
Yeah.
Okay. No problems? No explosions? No fires? They're still there?
No rockets?
The last time.
No lawsuit? Yeah, no rockets, no lawsuits, no dead people?
We had a flame failure, or an alarm. What was it? I think it's
Flame
Sunday.
failure.
Flame failure.
Ignition.
I don't remember what it was now. Ignition alarm failure.
They fell out your ignition?
Yeah. But
Oh,
it was here.
Hey, you guys you're under the manufacturer's warranty, so any issues, call us up. I mean, we'll come down, we'll troubleshoot it, we'll help you troubleshoot if you guys want to get involved, whatever you want to do. Okay?
Can we get one of those cards?
One of my cards? Yeah. Anybody else want a card?
Better take, I think we got yours, but I better make sure.
Yeah. Again, it's not very often you have somebody offering free training, so take me up on it. We'll gladly come down and teach you anything you want on boilers, on how to test that flue gas analyzation. It'd be very valuable to you. Okay. And still need to come down and do a hydronic balancing class with you guys. That's you got all these balancing valves out there. You guys do your own balancing, or you hired? How are you going to make sure that a year from now the new science building is still balanced?
It will.
It will be. Because Rocky Mountain did it, right?
Brian's our balancer.
That's one of the biggest problems we see in these hydronic systems is as soon as somebody goes out and uses a balancing valve, which you guys have manual balancing valves out here, as soon as they use that as an isolation valve, your entire system's out of balance. It does that? Let me turn back here and we'll just kind of review what we just talked about and show you what you're going to be looking for. So anytime these boilers are firing, look down this viewport. This viewport is where you'll see the flame. And it looks kind of like a honeycomb chamber down there, just a bunch of holes through it. And you'll see the flame down to the inside, and that's where you'll see the flame color. Make sure that the flame looks good here. If it doesn't, all the adjustments are made down here on this Siemens LM37 controller. Okay, and this is where you get into the back end, the code, and you enter the password, the 5555. 555. Oh, I'm sorry, yes, 58. Very good, thank you. That's where you make the adjustments here. This is the, right here, this valve right here is the gas serve valve. This is the air serve valve. So it's a constant speed fan, and then we're limiting the amount of air based on the level of combustion. So as this thing modulates, this is sending out a 4 to 20 milliamp signal to this valve and to this valve. So as we set up the 10 different points, we're setting this up at high fire all the way down to low fire, making sure that we have that proper interval combustion rate. Okay. All right. So that's where the adjustments would be made. This is where you're going to be looking to make sure that everything's good, and that's the daily. I'm sorry. That's the weekly. The daily, you're just observing the temperatures. Make sure that now this is kind of an interesting setup. You see that my set point is 180. And that we're measuring, this is on the discharge side of the boiler, we're measuring 117 degrees, and I've got a heat demand. Well, this is being bypassed, so don't pay any attention to the temperature that's being read here, it's the set point. Okay? These are receiving signals from that as the set point. So this boiler's saying, hey, I've got a heat demand, but this thing's not letting me on. Okay, so when that turns it on, then the boiler will go ahead and go through its modulation rate to satisfy the temperature that that's maintaining, and then everything will, and then if this boiler doesn't satisfy, then we'll turn the next boiler on and so on. Okay? So you just want to make sure that everything's working there. The high limit controls, you've got two aquastats right here. This is going to be your first stage, and this will be your last stage. You guys know how these operate? You've got these on every boiler by code. Per code, you have to have 2 safeties. Technically, this controller acts as a safety. So technically, I wouldn't need both of these. You need one that's an automatic reset and then one that's a manual reset. But because of the way this is wired, there's a potential of being able to wire this out of the system. So if that's wired out, because this would be your first safety. Once you hit your set point, then it would shut the boiler off. Okay, that's my first safety. The second safety, if that failed, would be this, and it would turn my boiler and shut everything down. But because I could potentially wire this out, I still have to have 2 that are hardwired in. So this one is currently set to 180, just over, it looks like 182 degrees. So if the water temperature, if this boiler is firing and the water temperature hits 182 degrees, the boiler is going to shut off. It's not going to really do anything to the controller, because the controller is going to say, hey, turn right back on. So the boiler is going to turn right back on as long as this has now reset itself because the water temperature dropped. So you could short cycle the boiler if this is operating too close to the temperature of what you want your water to be. But if you're telling me you're operating at 115 or so, that's why we've set this to 180. It doesn't have to be that high, that much of a difference. We recommend about a 15-degree difference. Because once the boiler shuts off, it can continue to build up heat. And between 10 to 15 degrees above that is what you should shoot for. So we've got this set to 180, and then we've got this set to just over 200. So it's about 200, it's right at 200. So if this fails, then this guy will trip the boiler off, and that's where you get the nuisance call. The boiler's in alarm. I can't get it to fire. This would be the reset button that you push, and if it clicks, then you know that it tripped on that. So you check the temperature. You know that it failed for a reason. Something's wrong here, something's wrong here. If you keep getting nuisance calls, check the difference between these two. They might be too close, so they may have adjusted that. Again, if you have a 5-degree difference, if this shut the boiler off, the boiler could keep heating up and keep tripping on this guy over here. Okay. Reduce the temperature settings necessary. Check temperature. You've got your air inlet here, which is coming. Does that come in from that parking area over there? That's where it pulls out the air inlet. And then your flue gases go out at the top. So you're definitely in 2 different pressure zones. So like we talked about before, you will see a change in combustion. But this is where you're going to want to check. Now, you know what? Actually, you'll notice this screw we had to back out on a couple of them because this air serve valve, notice where the air serve valve sits. As it would start to open and close, this was impeding its movement. So we had to back. I would be careful about doing this. You know, when people installed this, they screwed that in too close to where that's at. I wouldn't have done it that way. I would have used some sealant or something else. But on a couple of these, this was impeding that, so we couldn't get the boiler to operate. That's an example of an obstruction in the chamber here. So again, you're going to want to make sure that there's nothing obstructing in here, nothing obstructing in the back on the exhaust there.
So what's the error code that will throw if that happens?
The error code?
Or is there some sort of error code or when you're trying to start it up?
Well, yeah, what happens is this thing will, and maybe we'll turn one off if you guys want, but what will happen is the fan will turn on, the boiler will open everything up all the way. I think it's got a contact closure, make sure that it can open up all the way, and then everything will close back down where it needs to for combustion. So what happened is it would hit it, couldn't open, it would close, and then it just wouldn't start. So going back to the troubleshooting, it was fan will not start. You know, so we had to check, you know, some of that stuff. So the troubleshooting is pretty useful there. Here are your gas pressure switches. You've got your low and your high. This is your low, and this is your high. These have been set around the range that's labeled on your boiler nameplate. It says on there what the inlet gas supply pressure should be between your minimum and maximum, so that's what this is set to. It's not always the same per boiler. I don't remember if all 4 were the same on the nameplate. Sometimes there are a few inches of water column difference. So if you notice a difference, just check the nameplate on the boiler, make sure that it's in the range that it should be. But this is the reset button, so if you get that call, you know, you can't get the boiler to start, fan won't start, well, gas might be tripped. So check here, this little black button will be penetrated out, poking out, you just push it back in and you'll hear it click. If it tripped, and don't just say, okay, everything's fine, walk away. It tripped for a reason. You gotta go back to troubleshoot the system. Why is it tripping? Why did my gas pressure drop below? Or why did my stereo, why did my gas pressure jump higher than it needed to be? Okay?
What do we do when we check?
What do you do when you check?
Your
sit there,
Said it was a
test them,
high.
you test them.
Oh, to test them. Yeah, all you do is just open this up, drop it below where your gas pressure setting is, and then it should trip. So,
It's the same way we can check the height limits.
exactly, yeah, same way you check the height
Just
limit.
lower the
You
height.
just lower that below what the water temperature is, it should lock the boiler out. And that should be, those specific testing should be done once a year. Like I said, just check your limits. Inside the control panel, nothing fancy, this is your wiring. This is what's sending out the 4 to 20 milliamp signal to your valves up here. You've got your ice cube relays that are going on. The boilers have relays that are controlling the pumps, so when the boiler gets energized, then it turns the pump on. The pump pulls the water from the loop and back. I don't remember if these have flow switches. I don't think they do. So if a pump fails, the nice thing about these boilers is they hold a lot of water, so they're designed for zero flow through the system. So if the pump's not flowing, the boiler will turn on and it will heat up. The water will heat up pretty quickly, and then the controller will go ahead and shut it off, or it will shut off on these things here. So you'll want to watch that. If you see a lot of cycles on a boiler, you see the water temperature real hot on the boiler, check and make sure that that pump is being, the motor hasn't blown or something's like going on with the pump. Let's see what else we want to talk about. Any questions on what we're seeing here? You've got two gas regulators. This should be regulating it down to inches. So from pounds to inches, and this regulates us down from inches to inches to get us some fine-tuning on our gas supply pressure. Any questions on what's going on up front? If you can squeeze back here, I'll kind of show you what we talked about in class. These things are sized so to handle the load of two boilers. So that's why you've got two traps and then two receiving tanks. Again, you'll notice that you're coming off the back here. They did not give you any drain tees here because of the, you don't have the hard tee. Hopefully there's enough pitch so that that condensate can run back into the boiler. If you build up condensate back here, you will throw through this back stack. Okay?
Well, we don't want to go back and forth.
Yes. You want that condensate to run back in the boiler because then it's going to get down this bottom chamber and it's going to come out in the tube down here. So as long as everything's pitched back to the boiler, we're okay. We'll take rainwater. I mean, rain, melt the snow, that can come back to the boiler and then just go out the drain line at that point. But we don't have drain tees here, so just I would watch that. Just make sure that you're not getting any buildup in there. You see your drain tees up here where we're tying in the drain lines because you're going to be raining up top, and that's being run down to this same line, which is coming into this trap. Again, if that drops, you should get plenty of water to fill that back up to its level. As the condensate builds up, it'll travel through this pipe, fill this up down in here where it's neutralized, and then down to your drains. So you'll want to check the pH of this every 6 months at least. Make sure that you're somewhere around 6 to 7 pH. Okay? That's it.
Got one more question for you.
Okay?
In the event that we have a catastrophic problem with the EMS system and we need to run this in the manual, how do
you do that? How do you run it in local?
in local mode?
I have to look at the wiring diagram. I was kind of surprised not to see these with a 4-position switch.
Yeah.
Just a 2-position was a little interesting to me. Yeah. So it's on off is what it says, and when it's on, it's receiving a signal there. So it's
Gonna be done with the sequencer over here?
oh yes, yeah. The control panel you can force any boiler on. You can go manually turn it. I gotta give you training on that too. So it's all a touch screen interface. So you can look at this and say, okay, I I'd like to check my system status. So it shows your 4 boilers, and it shows that there's no call, your outdoor temperature, your loop temperature, your set point, and then your control variable. The control variable is what it's the control that it's going to be sending to the boilers to, to get these things on. This controller is not going to drive one boiler up to 100% with the others off. It'll drive it up to about 60%, then bring the second boiler on, take those to 30%, and so on, right?
Go up to 60 and then bring on the other.
Exactly.
And then
No boiler will go above that 60% level until all 4 are on and firing, and then it will. So you can get into boiler 1, and you can say it's enabled, it's an auto. I believe I can click on the auto and I can go manual. And you start. And then you can tell it to go to 100% firing. So this will take control. Now, if it was this, then you got to get into the wiring on that boiler and just disable that. You guys are wired with that lawnmowers on here, so the wiring, looking at the wiring diagram, you can look and say, okay, you got to set this and this. It's easily done, but there have to be some modifications made. And that might not be something. That might be something you want to add to the boilers. These are 3 position switch or 4 position switch. Does that make sense? So again, this is very user friendly. It's very hard to screw something up from here. So don't be afraid to just play around with it. So right now you're blinking an alarm, so there was an alarm. Go to the alarm status. Alarm history. So 212. Boiler 3 was in alarm.
that's why I had to press the alarm button on the.
And it cleared it?
And it cleared it.
If that becomes a common, let us know. Because we want to come down and check. It could be something to do with the. I had one boiler where we were getting air in, so the air source was true. Boiler 3, which one's boiler 3?